And that people might be joining later and watching on YouTube. Okay, I think we're live. Just checking. Okay. Okay, so hello everyone. Sorry, let me just switch screens quickly. Let's see what's going on. Okay, hello everyone, welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today we have the honor of having Dr. Johansson, a researcher from the University of Stockholm and the Oscar Klein Center for Cosmoparticle Physics. Dr. Johansson's research is related to cosmic dust and all sorts of supernovae, from the Zwicky Transient Facility, the public ESO spectroscopic survey for transient objects, and the Spitzer Infrared Intensive Transient Survey. Dr. Johansson, thank you so much for being so kind and having accepted to give us a webinar talk today on such an interesting topic. The floor is yours.
Thank you. Thank you so much for the invitation and the chance to talk to you guys about supernova and in particular infrared supernova observations. I will be sort of moving between supernova cosmology and good old astrophysics and astronomy. So we'll see. And I told Tasia that it's fine if you have any questions. Please raise your voice or raise the hand on Zoom if you have a question, and we can straighten out any question marks during the talk. And then I'm happy to take questions afterwards as well. Okay, so seeing through the dirt, a lot of the stuff I will talk about today somehow sooner or later relates to cosmic dust, how to avoid it, or sometimes how to detect it, depending on what you want to do. And I think this is one of my favorite nebulae. To me, it looks like a cat hitting a teddy bear. But if you switch from visible light to the infrared, progressively these beautiful colors from the intervening dust sort of disappears, but you also start to notice background stars that you couldn't see before. So that's one of the basic things with cosmic dust. It preferentially reddens and attenuates light at shorter wavelengths more, and its dust is more transparent than to infrared light. A sort of very sketchy outline of what I will try to mention in this seminar. I saw a fun thing on Twitter. You know, there are these different types of supernova papers that you come across, and you know, maybe I'm guilty of saying things like these two headlines: type 1a supernova are from two white dwarfs, or maybe not, but yeah, maybe. And things like these explosions are standardizable, except when they aren't, but we won't mention that, but I will actually mention that. So we'll start broadly, you know, talking about thermonuclear supernova or type 1a supernova. What is it that explodes and how? And then what they're good for, what we can use them as these sort of standard candles and measure distances in the universe. and then also turn towards the sort of astrophysical side of it, how we can learn what these explosions are from infrared, and in particular mid-infrared observations, for instance, with the James Webb Telescope. And lastly, if there's still time, might seem out of place here, but I will talk a bit about lensed type 1a supernova. Okay. So if you have been into astronomy for a couple of years at least, you are bound to have seen these cartoons here that I'm showing, and there hasn't really been much progress in the last 2 decades in this question. So type 1a supernova are thought to be, well, we have pretty good evidence that it's at least a white dwarf that explodes, and it does that by reaching this Chandrasekhar mass limit of roughly 1.4 solar masses. And then the question is, how does it reach this critical mass? Is it due to some sort of merger or collision between 2 white dwarfs, which is known as this double degenerate scenario? Or is it this other single degenerate scenario where you have a white dwarf that is more or less slowly accreting matter from another companion star, a main sequence star or some other massive star? And then among these bullets, I mean, there are a lot of question marks. What sort of triggers the explosion? Is it a sort of a fast detonation like a bomb, or is it a more slow burning deflagration that takes place on the surface of the star? And as always in nature, both these scenarios are possible, so probably there's a mixture of both happening, but somehow they seem to lead to a very sort of narrow range of luminosities of the exploding star. Okay, so this is a bit messy, but that's just the way it is. So we can talk about this thermonuclear supernova SU, and usually we're focused on this sort of middle part of the left figure. So it shows you the peak magnitude on the y-axis, and then on the x-axis you have something called the decline parameter, which tells you how fast the supernova declines from its peak brightness. So at the sort of lower decline rate, the slower evolving supernova we have, they are more luminous. So we call these 91T-like supernova. So the first sort of prototypical supernova was 1991T. And on the other side of this black line, which is in principle the foundation for supernova cosmology, that you can correct for the different decline rates and get some sort of standardizable peak magnitude. So you have fainter and faster supernova on this edge, but then all these colored blobs, fast decliners, 91BG-like, type 1AX supernova, O2. So you're seeing, so suddenly we have all these, this myriad of subclasses. So they are either subcategorized by their light curve properties, as you can see in this sort of middle panel. Either these very broad light curves like the yellow 1A CSM, which is also connected to their spectroscopic features that you see in the rightmost panel. So all these type 1A supernova have this prominent silicon absorption feature here. But based on this spectrum, you can sort of put a supernova in these different categories or different subclasses. Okay, so that's about the zoo, and that's in principle just stamp collecting or putting labels on things. It's not really telling you what's going on or what is a sort of useful, normal, good supernova for cosmology and what is just a peculiar weirdo. So hopefully we will get more into this. So this sort of circled region is what I will refer to as normal supernovae or normal type 1a supernova that you can use for cosmology. And then the hope, at least, is that these other subclasses might be some sort of extreme versions of the normal explosions that can sort of inform you about the parameter space of what kind of star explodes or how it explodes and so on. I think this is hopefully the only equation I will show, but it's basically the foundation for how we do cosmology with type 1a supernovas. I'm trying here to show you that in principle what we care about is the peak brightness in some filter that we measure through photometry. I'm taking images of the supernova as it rises and declines. And then we measure basically the shape of these light curves, which we call this X1 parameter, or I will maybe refer to as stretch, how stretched the light curve is in the sort of time axis. And then the second component is to measure the color of the supernova. So if you have different filters, some of them will be fainter in the blue or more bright in the red wavelengths and so on. So we can measure their color or their color excess. So it's a rather simple idea then that really has been sticking around since the 90s. And in some sense, you have to remember that we're actually physicists and not so much astronomers that came up with this standardizable form of sort of correcting for the light curve shapes and colors. But on the left-hand side of this equation, you have in principle just measured quantities like the observed maximum magnitude here, and the observed color and the observed stretch. And then they seem to follow a simple sort of linear relationship. So you can multiply this with some constant alpha, which is related to the shape, and beta, which is related to the color. And that you can use then to constrain cosmological parameters. So this distance, luminosity distance, DL. So when you do this, you can, in principle, get 7% precision on distance measures to any individual supernova. Okay, so then we observe a bunch of supernovae and we find them at different redshifts, and we measure their corrected distance modulus here from the supernova. So this is what we call then a Hubble diagram. So in this upper right figure, it's not the latest state of the art Hubble diagram, but it's I think the prettiest, the best looking one. But if we just look at some of the numbers here, so and it's kind of non-intuitive that if you start here in the low redshift sort of nearby regime, we only have today about 200 supernova with published light curves and good measurements. And then you have, for instance, the Sloan Digital Sky Survey had a supernova, a big supernova part that found supernova at this sort of intermediate redshift range around 0.2, 0.3 in redshift, and the supernova legacy survey in orange. And then, when you're out at redshift 1, you have to be in space in principle. So even though with HST you're doing infrared observations, you're still probing the rest frame optical here. So all in all, after almost 30 years or 25 years of supernova cosmology, we have about 1,700 supernova in total on the Hubble diagram. And I don't know if it's something to be proud of, but so in principle, there are 3 surprises coming out of supernova cosmology, and that is obviously the first surprise, that the expansion of the universe is accelerating, driven by some sort of dark energy component. But there are 2 current tensions, one can say, in cosmology, and one I will refer to as the mass step, and I will talk more about what this mass step means, and also maybe more known currently is the Hubble tension, meaning that the Hubble constant you get from the cosmic microwave background and the H0 that you measure from either Cepheids or other variable stars or stars in nearby galaxies, you get an H0 that differ, and the question is, are they significantly different? And so, for instance, the Cepheid measurements by the SHOES team, Adam Rees et al., now claim that there's a 5 sigma tension between these 2 Hubble constant measurements. So I'm going back to these equations. I didn't put it on just to have an equation, but so these 2 corrections that you do, the stretch corrections marked in green here, and then you make this color correction. But it's sort of standard issue in astronomy that you have to know something about the intrinsic color of your object, whether it's a Cepheid or if it's a supernova. So this last term is really a sort of convolution of some intrinsic color variation among the supernova, and then on top of that you have some dust extinction that you have to correct for. Okay, so this last beta times c parameter you can really think of as, you have to correct for the intrinsic color of the supernova and any intervening dust if it's in the host galaxy of the supernova, or even in the circumstellar environment of the progenitor system, intergalactic dust, Milky Way dust, and so on. So all of that has to be baked in. And I'm just showing here sort of a supernova spectrum here in black of a fairly high redshift supernova that was observed by the RACINS program with the Hubble Space Telescope. So you can see here that most of the flux of the supernova sits out here in the rest frame optical, or even at like 4,000 angstroms or something. So it's not a coincidence that most of the supernova cosmology that has been done is typically done in blue filters, and then the supernova gets intrinsically fainter and fainter towards the infrared. So thus they are fainter there and harder to observe. So there are some other nice perks of doing near-infrared observations of type 1a supernova, and that is, I think, very nicely illustrated in this figure that I borrowed from Casey Mandel's 2011 paper here. So the observed magnitudes, if we stick to the B band left panel here in the optical, in principle, you observe these red peak magnitudes for all the supernova versus this decline rate parameter. And then you have to correct for dust, and that lifts all the points up to these black dots. And then you have to correct for this blue line here, the linear relationship between the stretch or the width of the light curve and their peak brightness. Okay. But the nice thing is, if you observe them in the infrared, you see that the red dots, they move by some amount, but not by much, up to their dust corrected magnitudes, the black dots here. So in some sense, and also you see the slope of this blue line is much, shallower, or it's much flatter relationship here. So in some sense, they are already standard candles in the infrared. So they are not very sensitive to this decline parameter. And so that's a plus, and the plus is that they're less affected by dust absorption. And then, of course, the caveat is that it's trickier to do these observations. So you have the Earth's atmosphere is interfering, of course, and the supernova is fainter. And also, I think a lot of people don't forget to mention that the contrast also between the supernova and the host galaxy is worse. So the galaxies are typically brighter than in the infrared. So I can step one step back. So I mentioned you have this Hubble diagram, and you have some scatter here of about 0.13 magnitudes. But if you take all these supernova and you divide them up in two bins, you put all the supernova in massive galaxies above, let's say, 10 to the 10 solar masses in one bin, and you put all the supernova in the low mass galaxies in another bin. You see that there's actually a quite significant step here between the two. So meaning that after you've done all the corrections for stretch and color, let's see which way it goes now. The supernova in the high mass galaxies are on average roughly 0.1 magnitudes brighter than their lightweight low mass friends here. So it's been debated back and forth and sort of varying between different supernova samples and so on, what the size of this mass step is, and also the significance of this discrepancy here. But I think today most people are sort of agreeing that there is something we're doing wrong in the corrections. And then the question is, of course, is it due to intrinsic effect? In that sense, the supernova in massive galaxies might have different metallicity, might be in star formation rate effects, or in principle different supernova populations in low mass galaxies and high mass galaxies. Or it could be extrinsic effects, as I call it, and by that I mean, in principle, how we correct for dust in the host galaxy. So this is a line of thought I will sort of pursue from now on. And I usually like to show this comparison here of the night sky. So you see Andromeda there, which is fairly large if you could see it with your bare naked eyes on the sky. And I'm showing here the field of view of 3 different cameras. So one is no longer with us. It was the old camera on the Palomar Transient Factory, which covered roughly 7 square degrees of the sky, and surveyed the sky for let me see, more than 8 years. I think we were on sky. So I was working on the PTF project, and now since 2018 we have sort of updated the camera and put it on the same telescope, the 48-inch Schmidt telescope Mount Palomar. So with this camera we have a 47 square degree field of view, and I just checked today. So since 2018 we have found and classified 7,572 supernova, which is a lot. So you should compare them to the total 1,700 supernova that were on this Hubble diagram. And one thing that you're missing, of course, in this 2D image is the depth, right? So CTF typically goes out to 21st magnitude in, let's say, R band. So with LSST, which will have a smaller field of view, but will of course go much deeper with a sort of 10-meter size mirror instead of the 1.2 meter mirror on the 48-inch there. So the volume probe by LSST is of course much larger. So, but this is the sort of tool I use to find supernova now and in the past. And so we'll talk a bit about a paper that I had out last year where we followed roughly 40 supernova that we detected discovered with the PTF, and we obtained infrared observations with this rather modest telescope. It's a 1.5 meter telescope in Mexico, but it has this multi-band imager called Ratir, which goes from R band to H band. And not to get into details, but so a lot of the work in the near infrared field has been done by the Carnegie Supernova Project, which is this blue histogram here. So they really found a lot of them, or observed a lot of nearby supernova with super well sampled light curves from the optical to the infrared and so on. So we have a sort of more modest approach in the sense that we followed 40 supernova, but we tried to push the redshift range to go a bit further out. And we also tried to be less, what should I say, less biased towards finding supernova in massive galaxies. So CSP, almost all of their supernova were in these very massive red and dead galaxies. Whereas with PTF or CTF, which are sort of blind, untargeted surveys, you're finding supernova in teeny tiny host galaxies as well. So this is what the infrared Hubble diagram looks like. So I think at the time this was sort of all the supernova from the literature and from our sample together. So then we're talking about order of 200 supernova in total. So you have a really small scatter here around the Hubble diagram, but then we went a bit further and started dividing up our sample, in according to their host galaxy properties. So for instance, the stellar mass. So if you look at this supernova 14 BDN, it exploded in this blue star forming environment. And it was also a supernova that was sort of intrinsically blue, intrinsically bright, and so on. Whereas this other supernova, 13AHK, exploded in this red elliptical galaxy with, you know, this sort of dust lane visible here as well. And the nice thing about type 1a supernova is not only that they are standard candles, but we also call them standard crayons, in the sense that their colors are also very standard, or, you know, they are very predictable colors. So in principle, then, if you have a wide enough wavelength range of your observations, you can actually constrain the reddening parameters. So I show here the observed colors, or I'm cheating a bit here, so I'm plotting the extinction in each filter sort of normalized by the V-band extinction. And you can see for this supernova, the canonical sort of RV 3.1 that we usually measure in the Milky Way is not a very good fit. So this supernova wants to have an RV value that is higher, actually around 4, which is not unobserved. But for a lot of supernova, then we can measure in principle this RV parameter for every supernova individually. So that's what I'm showing here. And some of the people here might object. Now you can do that after the talk. You know, RV of 1, is that even possible? I think so. But in principle, we can measure the RV parameter for each individual supernova, and we actually see that these distributions for low mass galaxies and high mass galaxies are not the same. There's a large scatter, of course, but in principle, the observations indicate that on average, if you're in a massive galaxy, you tend to have a lower RV on average, and vice versa for low mass galaxies, you tend to have slightly higher RV values. So this has been noted, I mean, either simulated by people like Braut and Skolnick in their 2021 paper, but I guess people on the call are more, I heard a rumor that you are galaxy people. So there's this Salim 2018 paper where they look at attenuation curves of nearby galaxies, and you find sort of roughly the same trend, that high mass galaxies have this slightly lower RV, and star forming lower mass galaxies have slightly lower RVs on average. We can skip this. I'm running out of time. So what we then can do is that we look at each observed wavelength, and we compute this mass step, which was the Hubble diagram residuals for low mass galaxies and high mass galaxies. So what people have been seeing before are these gray shaded regions that the supernova are on average then that the corrected magnitudes differ by order 0.1 magnitudes. So this is what we also see, but so if you look at the red points, you see it as a function of wavelength, and regardless of sort of what kind of dust correction you do, they look standard. I mean, you don't have this mass step in the infrared, like let's say J and H band, whereas you do see the mass step if you're correcting all supernova with the same RV. While if you use this individually best fit measured RV for every individual supernova and correct using that, this mass step, I would say, vanishes, or it it gets less pronounced, I would say. So to be a bit Swedish, I will not say it's definitely dust, but I will say that it's most likely or probably dust effects that we're seeing. So this was something that the old astronomer Walter Bade realized a long time ago. So apparently a journalist asked him towards the end of his career if he could live his life again, would he still be an astronomer then? And his answer was that yes, but only if the ratio of the total to selective absorption, I mean, this RV parameter, is everywhere the same in the universe. So in, I guess, 6 minutes time, I will try to quickly just go through what I think is super exciting now. And especially since so I did work a lot with the Spitzer Space Telescope during my PhD and so on. And now, finally, since I would say middle of August, I'm also working on James Webb data. So we got the first data of the first mid-infrared spectrum of a type 1a supernova with Webb. I think August 13th. But as I'm trying to indicate with this figure, so I'm showing here the 4.5 micron absolute magnitude and the sort of time scale in logarithmic units here on the x-axis. Supernova in general, not just type 1a supernova, they really span this huge parameter space in absolute magnitudes and sort of light curve behavior. So type 1a supernova, these blue things, seem to follow a very tight and narrow range also in the mid-infrared. While core collapse supernova, these green dots, are a bit all over the place, which can be sort of due to dust formation and so on. And up in the upper right corner, you see type 2N supernova and something I called 1A CSM. So these are supernova that initially look like a normal 1A, but at some point crashes into some circumstellar material. And then they get super duper bright in the mid-infrared. So we'll just flash some very quick things here. So the program I referred to is to look at normal, I mean, type 1a supernova that we use for cosmological distance measures, is to observe them with the Webb telescope and get a spectrum. And there's really only 2 observed spectra of normal 1A supernova with Spitzer, and they look a bit like this. And I'm not showing that right now, but stay tuned for that. The Webb MIRI spectrum is very, very, very crisp. And yeah, I think, and so from those spectra, we will then sort of be able to identify not only these lines, which are much cleaner in the infrared, but you can also look at the line shapes and so on, which sort of constrains the explosion mechanism. Then I will sort of quickly jump through some individual weirdos that we, so these are all things we found with either Spitzer. So 2014 DT was a peculiar type 1A dubbed 1AX. So these are thought to be sort of weak explosions of white dwarfs, but the explosions are not strong enough to sort of disrupt the star. So you're left with a sort of a bound remnant star. So for this supernova, we saw a very strong infrared excess at sort of starting a year after explosion. So at 450 days, you have this additional emission out in the infrared, which gets stronger and stronger over the next sort of 100, 200 days. And the question is it a dust echo, or are we seeing sort of a wind from this remnant star? So these are things that we're hoping to be able to observe more in detail with the Webb. And here's another example that we found 2 years ago with CTF. So it looks, early on, it looked just like a, quote, boring, normal, vanilla type 1a supernova. So we got a spectrum here around peak, and we put it in the box with the other 5,000 supernova. And what then happened was that after roughly 70 days after peak, it did not evolve like we expected it to do, but it started plateauing or even increasing in brightness. And then over the course of a year, we saw this long-term sort of interaction powered light curve, and it was also booming in the mid-infrared in the WISE images that we analyzed. And if you look at the spectra here, you start to see these narrow, strong emission lines, and these are from helium, which we've never seen for a type 1a supernova before. So we have seen a few of these 1a CSMs, which are sort of crashing into hydrogen-rich material, but this there is some hydrogen here as well, but mainly extremely strong helium lines. So we think that this is a sort of the first cosmological example of a system like this V445 Puppis, which was the first helium nova discovered a decade ago. So this is an adaptive optics image of that system, which, so inside here sits a white dwarf that is secreting helium material from its companion star, and this will likely also go off as a type 1a supernova in the future. So I think I ran out of time. You guys think I should just mention these lensed 1As, or should we go to conclusion?
I think you're fine. Yeah, you can.
I can continue. Okay.
Yeah.
Cool. Oh no, not from start. Why did I do that? Sorry, I'm a bit sore in my throat here. Okay, so the last part, which might seem a bit disconnect, is suddenly I'm starting to talk about lensed supernova. So it might become apparent. So nature sort of gives us a rare chance that a supernova at some great distance here will have a foreground galaxy exactly along the line of sight, somewhere in between, and then you can have these strong gravitational lensing effects where the light is not only magnified, but also you get these multiple images of the background source. So people have seen this for quasars, and I mean, you also see this for galaxies that are bent into these beautiful Einstein rings. And I would say just by chance, so this was proposed by a Norwegian astronomer back in the 1960s, that in principle, if you have a time varying source that is strongly lensed, you can look at the arrival times of those images and measure the time delay, and that will in principle directly map to the Hubble constant. So that will give you a sort of an independent measure of the Hubble constant, regardless of the distance ladder measurements using, Cepheids and parallaxes and so on. So back in 2016, we detected a supernova, which is this image here, the central pixels of that thing. And when we got a spectrum of that, it looked like a normal type 1a supernova, except that it was at the sort of high redshift, otherwise unfeasible for the Palomar transient factory. So when we got Hubble images with high resolution, we could identify these multiple images of a supernova. So this supernova name was maybe not so well, not so easy to remember, but it was IPTF16GU, and we've written a whole bunch of papers on this single object. But so the hope was, of course, that we could we could identify these 4 images of the supernova, so that the host galaxy here is actually bent into this Einstein ring, and this blue thing that you see in the middle is the lens galaxy. So unlike with quasars, for instance, the supernova eventually fades and disappears. So then you can observe the lens and the host galaxy alone. If you go back a year later, and you can do the subtraction here, so you can see the individual 4 images of the supernova. And then we attempted to measure the time delay between the images here, which turned out to be very small. I mean, they were the time delays were less than a day or so. So within the sort of errors of our fits. We could also try to actually experimentally do the first sort of resolved spectroscopy of a supernova that was multiply imaged. So we could extract in principle 2 separate spectra, and we could compare, are these spectra of a supernova at different phases. So in principle, we could also constrain the time delay here, but with a sort of coarser resolution than the light curves. And then, as a sort of excuse for looking tired and unprepared, then we have been looking for 6 years to find the next lensed supernova, and of course, 6 years later, in the middle of my vacation, we found the second lensed type 1a supernova. So this one we were clever enough to dub Essence Wiki, which I think is a better sort of poster name. And it looks, we're observing this as we're speaking. We found it roughly 20 days ago, and we're getting lots of data. And to be honest, we're still trying to sort of understand what's going on, but it's definitely a type 1a supernova at redshift 0.35, and it's magnified by more than 3 magnitudes of lensing amplification there. So this has stirred a lot of excitement in the field. So if you want, you can stay tuned for any results upcoming there. So an attempt of doing a summary here. So type 1a supernova are very close to being standard candles in the infrared, and it's less sensitive to dust extinction. So you're getting this sort of clear view of the supernova looking through the dirt instead of being affected by it. But it also sort of indicates that you have to do the dust corrections much more carefully in the optical. And I mean, in the future, there are already ongoing programs to do rest frame infrared Hubble diagrams with the Hubble Space Telescope. But this will be great with the Roman Space Telescope that is upcoming. And then I just highlighted a few of the mid-infrared observations that we've done and that we're going to be able to do now with Webb, and the sort of prospects of mapping out different progenitor and explosion scenarios for all these kinds of cousins and weirdo siblings of the normal type A supernova. And then, yeah, so now we have 2 lensed type 1a supernova, and well, 2 is not a sample really yet, but we're expecting to find roughly 1 lensed supernova per year with CTF, or if you say like 1 out of 7,000 supernova, while you know, when LSST comes online, this number will grow to order of hundreds of supernova that are strongly lensed per year. So I think this is a really a field that will explode in the coming years. Okay, sorry for cracking up my voice here in the last seconds, but if you have any questions, I'm happy to try to answer them.
Thank you so much, Yobo, for the talk. We now have time for questions from the audience. Okay, I'll give a few seconds. If not, I have a bunch of questions for you. So can you go? Oh, okay, sorry. I'll take it from Rodrigo first, and then I'll go afterwards.
Thank you, thank you, Joe, for such a nice talk. I have a basic question in this on this last slide you showed us. To do the independent measurement of the Hubble constant, is there a minimum time delay required for in the lens supernova images?
So again, just the last words I missed. A minimal.
A minimum time delay.
Yeah. Well, so in principle, it has to do with how well, first of all, we can sample the light curve. So I failed to mention. So there's a nice thing about type 1a supernova. So if we go to our last the supernova that we discovered, we were actually we were very close to missing this. In principle, we could have caught it before it reached its peak, but you know, like I said, we were on vacation, we were not awake, so we missed the first peak. But since we're in the infrared, we have this secondary peak, so we get a second chance. So what we're trying now to do is to sort of sample this secondary bump. And then it's in principle just a matter of what's feasible, like how many visits with the HST or you know, adaptive optics with a 10-meter telescope you can do. So we're really struggling here to get the data, but we think that we can, in principle, measure this the time of the peak to sort of half a day precision or something like that. So then it depends what nature gives you. If it gives you a system with a 10-day time delay, then we can measure that time delay very well, and it would translate to a sort of H0 measurement that is good to like 5% or so.
Okay, I thought I missed that part. It's actually the time delay of the peak.
Yes. Yeah.
Okay. Now it's much clearer.
And this other method that that is a bit more experimental. We really want to be like where you would get, for instance, a spectrum of each of these 4 images. Then you would in the best of worlds, you would have a spectrum of the supernova at peak for image 1, and then maybe image 2 would be the same supernova but 5 days earlier or something like that. And and we can actually do spectral dating of type 1a supernova to sort of a day precision. So in principle, you could do this if you can resolve the images and you can get a spectrum early on. You could get the time delay from one single measurement in principle. And in principle, you should have lensed core collapse supernova, which are less standardizable in their luminosities, but also their spectral properties. So this sort of spectral dating could, I think, be the only way of getting a time delay for a core collapse supernova. Okay. It's really just measuring velocity differences in these absorption minima, for instance.
Okay. Well, thank you very much.
Thank you. But it was a good question.
I'll try and squeeze my question first.
Yeah.
Just one quick question before I go. So you had like these for the spectra that you showed just now. You had like these empty circles. Not this one for the.
Yep.
Next. Yeah. So you have the. What are the empty circles?
Sorry. Yeah. So this is just a screen dump from our sort of web page where we keep track of the supernova. So what I'm showing here is the magnitude on the y-axis and the days on the x-axis here. So today we observed the supernova in the so the yellow here is I band, red is R band, and green is G band. So yeah, but the only point I wanted to make is that we have the initial rise of the supernova here, and it peaked around 25 days ago. But then if you look at the other y-axis, which is the distance modulus, which is the observed magnitude and the distance. Sorry, it's the absolute magnitude. So it's the observed magnitude minus the distance modulus for a source at this redshift 0.35. So that implies that the peak magnitude of this supernova is -23, which is sort of 3.5 magnitudes brighter than the peak magnitude of a type 1a supernova. So in principle, just from this figure, you can read off the total magnification straight away, which is the other sort of nicety with lensed 1As, that you can break the sort of magnification degeneracy of the lens.
Okay, let me see if we have more questions. I'm checking YouTube. No. Okay, I have another question. You mentioned this when you were talking about RV.
Yeah.
And you said that RV equal to 1 is weird. Can you say a bit more about that? Because you had RV equal to 1 and you had like less than 1 also.
Exactly. So this is really for the hardcore astronomers. But in principle, everyone who's doing astronomy, right, you always have to correct for dust in the Milky Way, right? And then people out of old habit plug in RV equals 3.1. So which is true for most sightlines that we have studied in our sort of solar neighborhood, like along sightlines in the Milky Way, this RV parameter, which is, by the way, the ratio of the extinction here in the V band and the B band. So it's basically telling you about the slope here, if you see my cursor.
Mm-hmm.
So you can, I mean, so for stars in the Milky Way, this is normally done like you pick a pair of, you know, identical stars, but they have different colors. So therefore you can make out what the sort of the extinction as a function of wavelength would look like. So that's these, the solid and dashed lines are, there are these parameterized functions that describe what the extinction should be as a function of wavelength. And the parameter that you can vary is this RV parameter. So the black curve is steeper here, steeper towards the UV part, and that has RV 1.4. So and we've seen RV 1.4 for a lot of extragalactic supernova, and what some people complain about is that we haven't really observed any Milky Way sightlines with RV values this low. So I think the lowest RV in the Milky Way is something like 1.8 or 2 or something like that. So steeper, but not this steep. And we, I mean, if you look towards, I think molecular clouds in the galaxy, you tend to see these flatter extinction curves, and it's really just telling you about, I mean, in the long run, it's telling you about the distribution of grain sizes. So if you have smaller grains, you would have a steeper extinction curve, or if you have larger dust grains, the extinction would sort of flatten out, and you would get this, well, I mean, theoretically you could have gray extinction, which means that you attenuate dust equally strong at all wavelengths in principle. Yeah, so I think a lot of sort of observations show that RV is different in different sightlines in our galaxy, and they are different in other galaxies. So, you know, as a first guess, you can use RV 3.1, but in principle, it can be anything from 1 to infinity.
You had a value that was less than 1 also, didn't you?
Again?
You had a value that was less than 1 also.
I don't think so. Did I? Yeah, something approaching 0 here, but but this is, I'm drawing a dotted line here. So if your color excess is 0, or right, if your color excess is 0, then if you go to this figure, you still have measurement errors. So in principle, you can fit an extinction curve to noise, right? So if the color excess is small, your error bars on RV grow, and you're actually quite prone to fitting a small RV. It's kind of weird if your color excess is small. So that's when I'm sort of plotting color excess versus RV. So in principle, for 0 color, you cannot really constrain RV. But and if you conversely go to extremely high color excess, so we have a lot of supernova with a color excess that is greater than 1. But then it's a bias that in principle, we can only find supernova that are highly extincted and have a low RV. It's sort of the product RV times EB minus V that tells you what the absolute extinction is, right? So I guess, you know, if you have a supernova with a color excess of 1, but RV is 5, you would never be able to observe it. It would just be too too heavily extinguished. Yeah. So it's not super duper straightforward to do these RV measurements.
Thank you.
That answers the question.
Yeah. Yeah, I think it's okay. Do we have any more questions from the audience? Maybe if you're, I know we are a bit past the hour. I'll just give it another. Okay, so if there are no more questions, we'll wrap this up. The presentation will be available on our website and on Linja's YouTube channel. Thank you everyone for attending, and a special thanks to you, Joel.
Thank you.
Everyone have a great day, stay safe, and I hope to see you all again in our next webinar. Joel, will I see you tomorrow?
Yes, you will.
Okay.
Live.
Okay, see you then.
Should we go out for drinks then?
Wait, let me stop that.